Hello, everyone. This is one of my videos about statistics. And what I want to show you is how to conduct an observational study. The first thing that you should know about the analysis of an observational study is that it consists of two phases. First, an exploratory phase, and then second, an analysis phase where we do what is called matching. Okay. I will explain what matching is later in this video. Now, instead of doing both phases in one video, which will require a kind of long video, I have decided to do one video for each phase. So in this video, I will illustrate how to do the exploratory phase of one particular observational study. Then I will do a second video to illustrate the matching phase, okay? Perfect. So I have already prepared our notebook to do the analysis for this video. And I actually chose to include all the code in this notebook already. So every piece of code that I'm going to use is already in this notebook. Because guys, I really want to focus in this on this video on explaining the logic of the exploratory phase of an observational study. I want to focus on helping you understand and interpret all the outputs that we're going to get as we run the code, okay? So I thought that, writing all the code as I recorded the video will make the video kind of unnecessarily long, okay? So that's why I already included all the code. But obviously, don't worry, I will explain every code line so you understand what the code is for, okay? All right, guys, perfect. So the first thing that you should do if you want to replicate the analysis that I'm about to do is to install these two packages, the tidyverse and the DOS2 package. We need the tidyverse because I'm going to use some functions from the tidyverse to get some summary statistics. And we need the DOS2 package because the data we're going to use is part of that package. All right, so first you need to install these two packages if you don't have them installed already. And to install them, you need to run these two code cells, okay? But obviously, before running these two code cells, you need to remove the comments from the cells, okay? I don't need to install these packages because I already did. So that's why I'm not going to run these two code cells, okay? But definitely you have to if you don't have them installed already. After you install them, you need to load them by using the library function and the name of the package, okay? So first, let's go ahead and load the tidyverse from the code cell, load it, and then now let's go ahead and load the DOS2 package, okay? And load it, all right? Okay, so the data. Well, the data comes from a study by Costa et al. About welders' exposure to chromium and nickel substances that can cause inappropriate links between DNA and proteins, which in turn may cause genetic damage, okay? The data set is Costa and it's a data frame part of the DOS2 package. Because we already loaded the DOS2 package, we can access any data sets part of it, okay? And sure enough, here we're going to take a look at the data set by using the structure function and the name of the data set, okay? This is a data set with 47 rows. So we have data about 47 observations or people. And for each person, we have the person's age, race, smoking status, welder status, and DPC. I will explain what DPC is later in this video, okay? Now, what is the goal? What is the goal of the study? The goal of the study is to find out if the treatment, which is being a welder or not, has an effect on the outcome variable, which is the level of DNA protein cross-links in samples of white blood cells as an expression of genetic damage, okay? Now, let's define a few things. In this study, the treatment is the welder column. This one right here, okay? And it takes two values, no and yes. No means the person is not a welder. Yes means that the person is a welder, okay? Remember that a treatment is just simply the independent variable that we are interested in. So treatment is the independent variable which influence we want to study on the outcome variable, okay? Okay. In this example, the outcome variable or dependent variable, okay, same thing, is the DPC column, okay, and right here, and the DPC column measures the DNA protein cross-links in samples of white blood cells as an expression of genetic damage. So, the larger the value of the DPC column, the more evidence of genetic damage. Okay. All right. Now, this is an important clarification, guys. this is the goal of the study, right? Find out if the treatment, being a welder, affects the outcome, right? How are we going to accomplish that? Well, to find out if being a welder influences the level of genetic damage, we are going to compare two groups. The treatment group, like those who are welders, with the control group, those who are not welders, okay? And that's the way it works. In any case, in any example where you want to see if a treatment affects an outcome, you need to compare two groups. One group that received the treatment and the other another group that did not receive the treatment, called the controls. Okay, so we need to compare the treatment group with the control groups. In this case, we're gonna compare the welders with the non-welders. Okay. Perfect. Another clarification is this one, guys. I will refer throughout the video as I will mention the control group, or to refer to a control group, I will use the terms controls or non-welders. Okay, and that's something that you need to be aware of. So I'm gonna say the controls or non-welders, same thing. Okay, please, that's the same. They refer to the same thing. All right. So make sure you understand that. All right. So, and we also have covariates. Okay. What are covariates? Covariates are other independent variables, if you will. So, but these are independent variables that could be, okay, we don't know if they are, but they could be confounding factors. So the covariates could be the real reason for the observed relationship between the treatment and the outcome. Okay, so if in a given problem you observed a relationship between the treatment and the outcome, meaning like it looks like the treatment is affecting the outcome, the real reason for that could be one or more of the covariates. Okay, and that's something that we need to check for. Okay, and this problem, we have three covariates: age, race, and smoking status. Okay, all right. Now, how are we going to accomplish this goal? Find out if the treatment has an effect on the outcome. Well, guess what, guys? The gold standard, if you will, okay? The best method that we have to find out if a treatment affects an outcome are randomized experiments, or randomized control trials, okay? With a randomized experiment, we have, let's say, the highest chances of getting something that's called comparable treatment and control groups. Okay, that's kind of our ideal situation. We want to get comparable treatment and control groups. What do I mean by comparable? Well, comparable is a treatment and control groups, which only important difference is that one group received the treatment and the other one did not. Okay, that's what comparable means. Another way of explaining what comparable is that comparable would be a treatment and control groups that, at least on average, right, are similar with respect to all the observed covariates and also the unobserved covariates. Okay, what do I mean by observed covariates and unobserved covariates? So let's look at this example. In this example, um, two comparable groups means that welders and non-welders are similar with respect to age, race distribution, and smoking status. And those are the observed covariates, okay? So two comparable groups means, okay, welders and non-welders are similar, at least on average, with respect to the observed covariates: race, age, and smoking status, okay? But not only that, they are also similar. The two groups, welders and non-welders, are also similar with respect to any important unobserved covariates. Okay, and one thing that you should know is that there are usually dozens of uh, important unobserved covariates. Okay, all right. Now, in this example, what could be a possible important unobserved covariate? One that I can think of is the family history of this specific genetic damage. So here the dependent variable is the level of genetic damage, one specific genetic damage, right? So what is the family history of welders and non-welders with respect to that genetic damage? So ideally, for the groups to be comparable, the family history should be similar across, like between welders and non-welders, okay? Um, anyway, so if you use a randomized experiment, there are very, very high chances that you can get a comparable treatment and control groups. In other words, a treatment and control groups that are similar with respect to the observed covariates and also the unobserved covariates. That is great. That's what we get if we use randomized experiments. But guess what, guys? In this example, the data was not collected through a randomized experiment. It was not. The data was collected retrospectively. So the data was observed. Okay. So this is an observational study. Okay. And in an observational study, the treatment and control groups are very likely different with respect to both the observed covariates and the unobserved covariates. Okay. That's why if you want to analyze an observational study and then get valid conclusions, you need to do three things. So you need to take three actions or take three steps, okay? The first step is you need to check how unbalanced are the observed covariates across the two groups, okay? So that's the first step. Check for possible imbalance between the two groups with respect to the observed covariates. And that's what this video is about, okay? To check for imbalance between the two groups with respect to the observed covariates. That's a step number one. Step number two is if the observed covariates are actually unbalanced, we need to balance them by applying matching, okay? And that's what I'm going to do in video number two. And the third step that you should do when you do an observational study is you need to check to what extent the unobserved covariates affect the comparison between the treatment and control groups. And to do that, we do something called sensitivity analysis, okay? I'm not going to address sensitivity analysis for this example, but at least I wanted to mention that that's kind of the last and third step that you should do when you do an observational study. I might do a video about sensitivity analysis in the future, okay? Anyway, so as I just told you guys, in this video, we're going to focus on the first step. So we're going to do the exploratory phase where we do what? We check for possible covariate imbalance across the two groups. And by covariate, we mean the observed covariates, okay? So let's go ahead and address that, guys. Now, to check for possible covariate imbalance across the two groups, we need to do the following for each observed covariate, all right? So for each observed covariate, we need to do two things. We need to compute exploratory statistics illustrating the possible difference between the two groups. That's the first step. And the second step is we need to check if the difference suggested by the exploratory statistics is actually statistically significant, okay? So exploratory statistics, kind of to get an idea of how different the groups are. And then the second step is the difference suggested by the exploratory statistics statistically significant? Is it a real difference, okay? That's what we're going to do for each of the three observed covariates, okay? Now, before doing that, I like to start the exploratory phase by doing the following. I like to count how many treated subjects and how many controls, because ideally we want to have, for each treated subject, we want to have at least one control, okay? So we can do phase number two, the matching, in a more convenient way, okay? So to count how many welders and non-welders, I'm going to apply the count function on the welder column from the Costa data frame, okay? And sure enough, that will give me a count of how many non-welders, how many no's, all right, and how many yes, okay? So we have 21 welders and 26 non-welders. That's great because, there is, like every treated subject can be paired with a control, okay? That's what I can see from here. I'm okay because I can pair each treated subject with a control, okay? And that's what I'm going to do in video number two. In video number two, I will match the 21 welders with 21 controls, okay? All right, now let's go ahead and check for possible imbalance. Let's start with age. So is there an imbalance in age before we do the matching, which is what we're going to do in video number two. So let's check. And notice that this is, there is a question mark here. I don't know. I don't know if there is imbalance or no. I'm going to check for that, okay? And what I'm going to do is as I told you earlier, I'm going to compute exploratory statistics, okay? And for this, what I'm going to do is I'm going to apply the group by function to the welder column. So I'm going to group by welder status. So I'm going to get two groups, welders and non-welders. And for each group, I'm going to compute a few summary statistics like the mean, the median, and the standard deviation for each of the two groups. Okay. And that's what we get. Here we can see if we observe the average age for non-welders and welders. We see that welders are 4.5 years younger, right? So that's the difference in average, right? 4.5 years. So welders are 4, 4.5 years younger on average. And in terms of the median, welders have a median that is 3.5 years lower than controls, okay? So it looks like welders are younger than controls, right? But again, this is kind of exploratory statistics. So is the difference suggested by the exploratory statistics statistically significant? That's what we do next, okay? That's what we do next, all right? And to check for statistical significance in this case, I run the Wilcoxon rank sum test, which is just simply a non-parametric version of the two sample t-test. I prefer Wilcoxon than the two sample t-test because to apply the two sample t-test, we need the two variables, like the age for each group to be normally distributed. And, I don't want to really check for that. So I think it's just kind of more convenient and safer to apply Wilcoxon rank sum test in this case, okay? Now, why am I using alternative grader? Well, the exploratory statistics are suggesting that the average and median for welders is lower, right, than for non-welders, right? So I want to use an alternative hypothesis that checks specifically for that. See if welders are less than non-welders. Now, this is what you should notice, guys. Welders less than non-welders is the same as non-welders greater than welders, right? Guess what? It is actually more convenient in this example to set the hypothesis like that, like non-welders being greater than welders, okay? Because why? Because R uses the first category as the reference, okay? The first category for the welder column is, as you can see here, is known, meaning non-welders, right? So when we do alternative grader, what R will do is it will check if the first category, non-welders, is greater than the second category. So if we say alternative grader, R will check if the reference category, the first category, non-welders, is greater than non-welders. That works for us because checking whether non-welders is greater than welders is the same as checking if welders are less than non-welders. So that will work, right? That will do the job, all right? So we run the Wilcoxon rank sum test. And here we can have fun like interpreting the test statistics and what it means and all of that, but we're going to focus on the p-value. Remember, if you want to check for statistical significance at the end of the day, what you need to do is you need to um, see how statistically significant the results are. And to do that, what you do is you compare the p-value of the test with alpha or the significance level. Let's assume that we are using an alpha or significance level of 0.05. And if we assume that this p-value is obviously less than 0.05, so what happens with the p-value is less than alpha? We have support for the alternative hypothesis. So in this case, we can claim that the age of non-welders is statistically higher than the age of welders, okay? So these results confirms the results from the exploratory statistics that suggested that welders were younger, right? Remember, non-welders higher than welders with respect to age is the same as saying that welders are younger than non-welders, okay? So perfect. So we found an imbalance in age between the two groups. And of course, we're going to address that later, okay? Let's move on to the second covariate, which is race, okay? And again, we're going to do two steps, exploratory statistics, then the test, okay? So Here again, it's a kind of a question mark. We don't know. Is there an imbalance in race before matching? All right. So for the exploratory statistics, this is what I did. I guess to illustrate this, I'm gonna break this down in steps. You know what I mean? Because it will be easier for you. So let's see what this does. This will get the count um, for each combination of welder and race, right? So we have 5 non-welders that are African Americans. By the way, the races are A, African Americans, C, Caucasians, okay? And then so on and so forth. We get, we have 21 non-welders who are Caucasian, and so on, so on, so forth, okay? Now, since I only want to see the race distribution for controls for non-welders, I want to filter for that. That's what I'm doing here. I'm filtering for non-welders for the controls, okay? So that's why I have the filtering, all right? And sure enough, let me move this down. Sure enough, if we do that, we only get the non-welders or the controls. That's what I want. But the thing is, I don't want to see only the counts. I want to see the proportion. So that's why this mutate function will compute the proportion. We'll create a new column, proportion, computing the proportion following that formula, okay? And let's do that. And let me move this down. And sure enough, now we get not only the count, but also the proportion. And the last step is just because, this is kind of redundant. Since I'm saying like here, I'm saying that I want to get the race distribution for controls. I don't want to see that column. So to remove that column, what I do is I select the columns that I want, okay? I can also do this differently. I can deselect the welder column, but that's okay. That will work as well. Anyway, so that's what I have, okay? And yeah, so I just repeat the same thing for welders now, okay? Same idea for welders, okay? This is for welders, and let me move this a little bit up, and that's what I get, all right? So what do we see here, guys, in terms of the difference between the two groups? So, well, in terms of African Americans, we can see that 19% of non-welders are African Americans compared to 10% of welders are African American. Okay. So African Americans seems to be more prevalent among non-welders, right? And obviously the opposite is true for Caucasians. So they seem to be more prevalent among welders. So 90% Caucasians among welders, 81% among non-welders. Okay. Perfect. But again, these are exploratory statistics. So is the difference in race suggested by these exploratory statistics statistically significant? That's what we do next, okay? That is what we do next. Now, to find out if the difference in race across the two groups is statistically significant, I use a Fisher test, actually called Fisher exact test, okay? So one thing that you should know is that Fisher exact test is applicable when we have two categorical variables with two categories each. That's exactly our case. We have two categorical variables, race and welder status, and each has two categories. Caucasian, African American, and welder is no and yes. Okay, so Fisher exact test is applicable. Now, what does it do? So, what does Fisher exact test do? With Fisher exact test, we can let's see, we can check, okay, whether the proportions of the first let me see how to say this. So we can check whether the proportions for the categories of the first variable change significantly across the second variable. I think that's a way of framing this. So when we apply Fisher exact test, we can check whether the proportions for the categories of the first variable change significantly across the second variable. If we try to translate that to this problem with Fisher test, we can check whether the proportion of African Americans and Caucasians, the first variable race, change across welders and non-welders. That's the second variable. Okay. Perfect. Now, to understand why I used alternative grader, we should take a look at the frequency table for the welder and race column. That's what I'm trying to do here with the table function. Okay. Now, when we use alternative grader, the Fisher test checks whether the first column category, okay, here we have two categories in the columns, right? It checks whether the first column category, again, if we are setting alternative grader, it checks whether the first column category is more prevalent in the first row category than in the second row category, okay? Now, if we apply that to this problem, Fisher test by using alternative grader will check if the first column category, African American, is more prevalent in the first row category, non-welders, than in the second uh, row category, welders. Right? That's exactly what the exploratory statistics are suggesting. Right? Exploratory statistics are suggesting that African Americans are more prevalent among non-welders than among welders. Okay. Well, if we do alternative grader in this case, that's exactly what we're going to check. Okay. All right. So let's go ahead and run the Fisher test and see what happens. Okay. Again, we can have fun interpreting all the output from that test, but we're going to focus on the p-value because we're assessing statistical significance. So p-value 0.307, obviously greater than alpha. So because p-value is greater than alpha, we cannot claim that the proportion of African Americans is statistically higher among non-welders than among welders. We cannot claim that. Okay. So in conclusion, the difference in proportions for the two races between welders and non-welders is not statistically significant. Okay, so the difference observed in the exploratory statistics it's not a statistical significance. Okay, all right. So we did not find a significant imbalance with respect to race. How about the third covariate, which is smoking status. Okay, so for smoking status, I kind of do the same thing I did for race. So I kind of computed the same summary statistics. All right, there you have it. So 16% of non-smokers among non-welders and 35% of smokers, and for welders will be 48% of non-smokers and 52% of smokers. Okay, so what do we see here, guys? So 52% of smokers among welders compared to 35% of smokers among non-welders. So it seems like smokers are more prevalent among welders, right? And the other way around. So non-smokers seem to be more prevalent among non-welders, okay? And well, I will actually check for that. So in this case, it's more convenient to check whether non-smokers are more prevalent among non-welders, which again is the same as checking if smokers are more prevalent among welders. Okay, so okay, to check for that, I'm going to use alternative grader because for the same reasons that I explained for the race column. To check if non-smokers are more prevalent among non-welders than among welders, it's this is the right choice, so alternative grader. Okay. All right. Let's run this test. And again, let's focus on the p-value to check for possible statistical significance. And the p-value is 0.1768, so greater than alpha. So because p-value is greater than alpha, we cannot claim that the proportion of non-smokers is statistically higher among welders than among, I'm sorry. We cannot say that the proportion of non-smokers is higher among non-welders compared to welders, okay? That's what we try to see. That's what the exploratory statistics are suggesting, but the Fisher test is not giving us enough evidence for that. So we cannot claim that non-smokers are more prevalent among non-welders than among welders. Okay. In short, the difference in smoking status between welders and non-welders is not statistically significant. Okay. All right, guys. So at this point, we are able to conclude the exploratory phase, and we should say a few things to conclude. Remember, we were checking for covariate imbalance, all right, between the two groups, right? So a few things. First, um, the the welders, so the treated subjects, right? The treated subjects and the non-welders differ significantly with respect to age, okay? Welders are younger on average than non-welders, okay? So that's a significant difference between the two groups. Another thing that we can say is that the difference between the two groups with respect to race and smoking status is not statistically significant. So there is not a kind of important imbalance with respect to those two covariates, okay? Now, this is the thing, guys. Remember that the goal of this study was, right, to find out if being a welder has an effect on the outcome variable, genetic damage, right? And this is the thing. We want to compare if the genetic damage between welders and non-welders, uh, it's due to, right, the welders being exposed to chemicals, right? But this is the thing. Given that the two groups, given that welders and non-welders differ significantly in age, if we go ahead and run a test and find a difference between genetic damage between welders and non-welders, we could be tempted to justify that difference by the age, not by the fact that one group is welders and the other one is not. You know what I mean? So we want to compare welders and non-welders with respect to genetic damage, but they differ with respect to age. So there's always a temptation to say, yeah, the difference in genetic damage that we are observing between welders and non-welders is not because of what they do. It's not because welders are exposed to chemicals. It's maybe because of age. Okay, that's a rival. That's a possible rival explanation. So we need to address that imbalance in age. So if we want to compare welders and non-welders with respect to genetic damage, we need to address that imbalance in age. Okay, and that's what I'm gonna do in video two. In video two, I will match the 21 welders with 21 non-welders, and I'm gonna try that both groups do not exhibit any imbalance in age, and obviously they should not exhibit any imbalance for the other two covariates either. Okay, and as you will see, I will accomplish that by using the propensity score. Okay, I'm gonna do that matching by using the propensity score. And as you will see in video number two, once the groups are matched, I will be able to confidently compare the 21 welders and the 21 non-welders with respect to their genetic damage. Okay. Okay, so this concludes video number one, the exploratory phase, and I hope you learn the steps that you should follow if you need to do an exploratory phase for an observational study. Okay, all right. That's all for this video, and I will see you in the next video.